Ah! Turn that off. Throw a baseball and catch an exercise ball? Believe it or not, interactions like this happen all the time, at least on the subatomic scale. So it turns out that a very special type of particle called a neutrino does something just like that. And neutrinos are particles in the Standard Model, which is a model that describes the smallest particles that we know of currently. And these particles make up everything that you can see around you, and they cannot be broken down as far as we know. So neutrinos come in three types, or as physicists call them, flavors, like the flavors of an ice cream cone. There's the electron neutrino, there's the muon neutrino, and there's the tau neutrino. And these three types have a strange property that as they travel through space, they can change into one another. So how can this be? Well, the answer lies in the mysterious world of quantum mechanics. Now, the first key quantum concept we're going to need to understand is superposition. According to this, a neutrino can be in a mixture of possible states, like an ice cream cone can be both vanilla and chocolate at the same time. And this leads to the second key quantum concept, which is collapse. Although we might have a neutrino that's both electron and muon at the same time, when we measure it, quantum mechanics says that we can only get one or the other, either 100% electron or 100% muon. So now things get really strange. So it turns out that there are three different masses that a neutrino can have, but these aren't the masses of the three different flavors of neutrinos. It turns out that we can know the mass of a neutrino, but not its flavor, or the flavor of a neutrino, but not its mass. So the way this works is because it turns out that there are three different types of neutrino with exact masses, which we call the 1, the 2, and the 3 neutrino. But these neutrinos are not the three different flavors of neutrino. Instead, they are superpositions of them. Each one is a superposition of the electron, muon, and tau. So also though, we can have the electron, muon, and tau, but those can also be thought of as superpositions of the 1, 2, and 3 states. So in this way, both are superpositions of each other. Now we're almost there. It turns out that the 1, 2, and 3 neutrinos are easier to work with. And this is because quantum mechanics tells us that particles act like waves, and the 1, 2, and 3 neutrinos have very simple waves. But when we add these together to form one of the flavors of neutrinos, something interesting happens. They start to interfere, and this causes the wave to oscillate between the different flavors. So here, we might start out as an electron neutrino, but get to a part in the wave that is very little electron neutrino and mostly a muon or tau neutrino. And this is what causes neutrino oscillation. This is actually a slight simplification. In reality, the 1, 2, and 3 neutrinos waves are actually spinning circles, but we still add them to get the waves for the electron, muon, and tau neutrinos, and when we do, we get interference. So an electron neutrino can naturally flow between being purely electron and a mixture of the different the flavors of neutrino. And that is what causes neutrino oscillation, because we can go from mostly electron neutrino to be mostly muon neutrino to mostly tau neutrino and repeat. And if we measure at the right time, we can get a different neutrino than the one we started with. So that's neutrino oscillation. But why does this matter? Well, neutrino oscillation is very special, and it's starting to tell us that neutrinos might be the reason that there's matter in the universe. So neutrinos really do matter.